All over the world, people are drinking water they believe is safe but actually isn't. And often, the danger isn't what you can see, smell, or taste, but it's what you can't. One of the most dangerous examples? PFAS, or per and polyfluoroalkyl substances, better known today as forever chemicals. These are synthetic compounds found in firefighting foams, non-stick pans, water-resistant clothing, and food packaging. They've been used since the 1940s, and they're still everywhere. Studies show that exposure through contaminated drinking water is a major reason why PFAS are now present in the blood of almost all tested populations globally. And the health effects? Cancer, liver damage, immune dysfunction, and hormone disruption, among many others. In many middle-income countries, including the Philippines, communities are located near industrial zones, agricultural runoffs, and aging water infrastructure. A 2024 study detected PFAS in surface waters and wastewater effluent near urban and peri-urban sites across the nation's capital, Metro Manila. And this is not localized. Across the nation, water resources have been found to be contaminated with forever chemicals, specifically in dams that cater to drinking water demands. In the Philippines, which experiences an average of 20 tropical cyclones annually, floodwaters can mobilize contaminants from industrial, agricultural, and landfill sites, making them harder to track and control. The gold standard for detecting PFAS is through liquid chromatography mass spectrometry, or LCMS. It is highly sensitive, but also expensive, slow, and limited to well-equipped laboratories in capital cities. The archipelagic nature of the Philippines makes this even harder. With over 7,000 islands, getting reliable, centralized testing to every affected area is simply not feasible. So what kind of solution do we actually need? One that's fast, affordable, and doesn't rely on distant labs or expensive machines. A solution that works where the problem is, not days or islands away. So, we built one. A simple color-based sensor designed to detect PFOA, one of the most harmful PFAS chemicals found in drinking water. At its core are silver nanoparticles billionths of a meter wide. We coat them with chitosan, a natural polymer extracted from crab shell waste. When PFOA is present in a water sample, it interacts with the chitosan coating, changing the nanoparticles' behavior. Red means the nanoparticles aggregated and the sample is safe. Yellow means PFOA is present and prevents aggregation of silver nanoparticles, a color detection that appears within a minute. And the color change isn't just on or off. It shifts gradually as the PFOA concentration increases. The varying color intensity gives a visual estimate of how much is present. Even without instruments, users can tell not just if contamination exists, but how severe it might be. Selectivity is also important as water contains many similar compounds. Here we see that only PFOA triggers the distinct color shift, ensuring accurate detection in complex samples. This is proof of our facile, low-cost tool precise enough to estimate concentration and selective enough to detect PFOA in complex water samples. And this is just the beginning. Right now, our sensor targets PFOA, but the vision goes beyond that. By changing the bio-based coating, we aim to detect other contaminants like heavy metals, pesticides, or antibiotics. In one of our other works, we have successfully detected heavy metal nickel in tap water using citrate-stabilized silver nanoparticles, proving the sensor's modularity. Like the crab shell-derived chitosan, these coatings can be sourced from plant waste, fruit peels, or other local byproducts supporting SDG 12, responsible consumption. The long-term goal is to build a flexible, low-cost platform that enables local communities to monitor diverse chemical threats, advancing UN SDG 6 or Clean Water and Sanitation, one test at a time. The sensor is made through a one-pot synthesis using just a stirrer, not needing complex equipment. It is also stable for weeks, making it usable for routine water monitoring but especially valuable during post-disaster situations when contamination risks are highest. In the Philippines, local health units already play a key role in both public health and disaster response. With basic training, barangay health workers and community responders can prepare and use this sensor on site without waiting for lab results. It empowers them to act faster, respond locally, and protect public health, advancing both SDG 3 and SDG 13. This project might have begun in the lab, but it's built for communities, a low-cost, locally sourced sensor for real-world water safety. Useful for routine monitoring and essential when testing access is limited. It's a step toward faster, local responses starting in the Philippines and scalable beyond. All over